A solution of nitric acid is made by dissolving that many moles of the liquid acid to form that volume of concentration. What is the mass of nitric acid that would be required? So we say mass is equal to number of moles times molar mass, and that's equal to 0,2. They've given me that. And the molar mass of nitric acid is HNO3, so it's 1 plus 14 plus 48, and I land up with 63, and that becomes 12,6 grams. Determine the concentration of the resulting nitric acid concentration. If you're not writing formulas down, I can't give you marks. Number of moles divided by volume. They've given me a number of moles, they've given me a volume, and I land up with 0,4 moles per cubic decimeter. Remember, minus 3 over there, it's per cubic decimeter. Determine the concentration of 12 grams of sodium hydroxide dissolved in 500 centimeters cubed of water. The first thing to do is to work out my number of moles. Mass over molar mass, which is 12 that they give me. The molar mass of sodium hydroxide is 23 plus 16 plus 1, which is 40, and that is 0,3 moles. You then are going to say concentration is equal to number of moles divided by volume. 0,3, I have to change the 500 centimeters cubed into 0,5 decimeters cubed, and I land up with 0,6 moles per cubic decimeter. 34 grams of silver nitrate is dissolved in water to make up a solution of that volume. Calculate the concentration. Better work out the formula for silver nitrate. Silver has a valency of 1, nitrate has a valency of 1, so it's AgNO3. The molar mass of that, I think, is 107 plus 14 plus 48, and it turns out to 170. So I can say number of moles is equal to, again, I must write out formula to mass over molar mass. I've been given 34 grams, the molar mass is 170, I get 0,2 moles. Concentration, number of moles divided by volume, 0,2 moles divided by, convert that, 0,2 decimeters cubed, and I get 1 mole per cubic decimeter. I've got 44 grams of magnesium fluoride, and they're dissolved to make up a certain solution. Calculate the concentration. First thing I need is the molar mass of magnesium fluoride, and it turns out to be 24,3 for the magnesium plus 2 times 19, and I get 62,3 grams per mole. Number of moles is equal to mass over molar mass, which is 44 divided by 62,3, and I land up with 0,7 moles. Concentration, again I write out my formulae, number of moles divided by volume. These two formulae, by the way, are on the information sheet. There is no excuse for getting them wrong. So it's 0,71 divided by 0,75. I've had to convert the 750 centimeters cubed. 0,94 moles per cubic decimeter. That is the solution now. The next thing I have to do is I need to work out the magnesium ions, and magnesium fluoride is to magnesium as 1 is to, there's only 1 in there, 1. So 0,94 to 0,94. The concentration of the magnesium ions is 0,94 moles per cubic decimeter. I can write that by putting a square bracket, Mg2 plus. The square bracket means concentration of the magnesium ion is Mg2 plus. What about the fluoride ion? Magnesium fluoride is to fluoride, sorry, that would be better, is to fluoride as 1 is to, in every one of those there are 2 fluoride ions. So if I had 0,94, I now have double that number, which is 1,88. And therefore the concentration of fluoride ions is equal to 1,88 moles per cubic decimeter. If the concentration of 300 centimeters cubed of copper chloride is that, calculate the volume of water that needs to be added to reduce the concentration to something else. Remember my little box system. I take a look at the 2 boxes and I see what information I have about each one of them. And the first one is I have got 300 centimeters cubed, so I'm going to say volume is 0,3 decimeters cubed of a concentration of 0,36. and I need to change that concentration into 0,01, and I am interested in my volume, and my number of moles is what I'm going to look for because I've got enough information to be able to do that, and the number of moles will go across to the new container. So let's see what we've got in the original container. We have got number of moles is concentration times volume, which is equal to 0,36 times by 0,3, and that is 0,108 moles. So in here I've got 0,108 moles. I carry it across into this container, 0,108 moles. And I now work out what volume would I require for that concentration. So volume is number of moles divided by concentration, and it's 0,108 divided by 0,01, because that's the concentration that I'm looking for, and I find my volume comes out to be 10,8 decimeters cubed. But I already had 0,3 of those, so how much water must I add? 10,8 minus 0,3 is 10,5 decimeters cubed that I would need to add to that solution. We've got Curiosity, the Mars rover, finds a rock on Mars and determines its weight to be W. The radius of Mars is R. The space team picks it up and takes it to planet Beta, where the weight of the rock is now 8W. So let's first look at what happens on Mars. W is equal to G, the mass of Mars, times the mass of the rock, divided by the radius of Mars squared. We're now on a new planet, and we're going to say 8W, because the weight is now 8 times. The radius of planet Beta is half of that of the other planet, so I'm going to do that, is equal to G. They haven't told me the mass of the new planet, but I do know the mass of the rock is unchanged, so I'm going to say X times the mass of the new planet. Let's see what comes out of that. I get 8W is equal to, bring X to the front, GMM, and a half squared is a quarter to the front, R squared. This whole thing over here is W. Therefore, and when I've got a quarter at the bottom, it turns into a 4. XW is equal to 8W. What must X be? X must be equal to 2, and therefore my mass of my new planet is 2m. We've got a gravitational force of attraction between two satellites is F. Again, F is equal to G, M of the first satellite, M of the second satellite, the distance between those satellites squared. The distance between the centers of the two satellites doubles. So I'm now going to say I have got something is equal to G, M1, M2, 2R all squared. So that turns out to be a quarter of whatever my old force was, G, M1, M2 over R squared. That is actually equal to F. Remember, here it was. And therefore, I have got a quarter of the old force. The next one wasn't particularly challenging. I'd given you all of the conversion factors, and yet somehow people chose to ignore those, but we'll carry on with that. Calculate the gravitational force between two objects with masses. So F is equal to G, M1, M2. I'd like you to notice that I write out the formula in order to get some marks, hopefully, even if I stuff it up. 6,67 times 10 to the negative 11. The first mass is 124 megagrams, and they tell me mega is times 10 to the 6. So I go. Now the problem is we don't actually want to go to grams, we want to go to kilograms. So I now need to change this very slightly, and I need to go from mega to kilo, which is only times 10 to the 3. So I'm going to go 124 times 10 to the power of 3 and 244, and it's going to be times 10 to the power of not 9, it's 10 to the power of 6. Why? Because I only want to get to kilograms. I don't want to get all the way down to grams, and I divide all of that by my 15 kilometers, which does need to get down to meters, and kilos times 10 to the 3. So it's times 10 to the 3, and then I mustn't forget to square the entire thing. And I land up with 8,97 times 10 to the negative 6 newtons. The first chimpanzee to be launched into space was named Ham. He was born in 1956 and sent into space in 1961. Ham was sent 753 kilometers above the surface of the Earth, and he had a mass of 40 kilograms. State Newton's universal law of gravitation. You have to learn your laws, guys. You can use this as a helpful hint, but you can't not know what the law is. So you would need to state the following. Firstly, you need to say that any two objects in the universe attract each other with a force. That force is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Look at your definition carefully and learn them well. 9.2, calculate the gravitational force acting on Ham when he was that high above the Earth. So the gravitational force, and you've got to know the difference between gravitational acceleration, which is g, and it's in meters per second squared, and gravitational force, which is the whole bang shoot. So it's g m1 m2 over r squared. The big thing here is to have added your radius of the Earth and the distance that Ham was above the Earth, and you get 7,124, and then that's got to go into meters because it's kilometers, so 10 times 10 to the power of 3. Substituting in 6,67 times 10 to the negative 11. The mass of the Earth has been given to me in kilograms already. The mass of Ham is in kilograms already. 7,124 times 10 to the 3, and we have to square all of that, and we come out at 315,42 newtons that Ham was attracted to the Earth with. Then it says Ham has a weight of 392 newtons on Earth. How much does he weigh on a planet that has twice the mass of Earth? So then his weight will be twice as big because it's directly proportional to the mass of the planet. So we're going to go 392 and we're going to multiply it by 2. And a radius 3 times that of Earth, so I need to divide by 3 squared because it's the radius at the bottom that has to be 3 squared. So when I get that, I find that his new weight would be 87,11 newtons.